Imagine a world so distant that sunlight takes over 4 hours to reach it. A realm of ice and gas swirling in the outer fringes of our solar system. This is Neptune, the enigmatic ice giant, a planet so remote it's often overlooked in the cosmic spotlight stolen by Jupiter's grandeur or Saturn's radiant rings. Yet, in the summer of 2025, Neptune seized the universe's stage in a spectacle of raw power and cosmic drama, captured in vivid detail by the James Webb Space Telescope. A massive object ripped from the solar system's farthest reaches, slammed into Neptune's atmosphere, unleashing an event so staggering it left astronomers breathless. This wasn't just a collision, it was a window into the violent, ever-evolving nature of our cosmic neighborhood. Buckle up, because we're diving into a story that spans billions of miles, millions of years, and the very forces that shape planets, stars, and perhaps even life itself. Stick around to the end and let us know in the comments what you think this cosmic event means for our understanding of the universe. Picture this. It's July 2025, and the James Webb Space Telescope, humanity's most advanced eye in the sky, is peering into the outer solar system. Its infrared vision, capable of slicing through the darkness of deep space, locks onto Neptune, a planet nearly 2.8 billion miles away. Suddenly, its instruments detect something extraordinary. A burst of heat, a ripple of chemical signatures, and spectral lines that scream of an event unlike anything seen before. Neptune, the serene ice giant, has been struck by a massive object, possibly tens or hundreds of kilometers wide, in a collision that released energy equivalent to millions of nuclear explosions unfolding in an instant. The data streaming back to Earth tells a story of shockwaves tearing through Neptune's atmosphere, exotic ices vaporizing, and a chemical scar etched into the planet's swirling clouds. This wasn't a fiery Hollywood explosion. Neptune, with no solid surface, is a world of dense gas and ice, its atmosphere a turbulent ocean of hydrogen, helium, and methane. When the intruder, a rogue comet or icy body from the Kuiper Belt, plunged into this gaseous sea, it didn't crater the planet. Instead, it compressed the atmosphere, sending supersonic shockwaves rippling outward. The object fragmented, dissolving into Neptune's depths, leaving behind a trail of carbon-based molecules, ammonia, and possibly carbon dioxide. These chemical fingerprints, glowing in Webb's infrared gaze, are a testament to the intruder's origins, a time capsule from the solar system's primordial past. This was no ordinary event. It was a cosmic collision that rewrote Neptune's story in real time. What makes this moment so gripping? It's the sheer improbability of catching it. Collisions of this magnitude on Neptune are rare, happening perhaps once every few centuries or millennia. Yet Webb was watching at exactly the right moment, its pristine vantage point at Lagrange Point 2 offering clarity no Earth-based telescope could match. This wasn't just luck, it was a triumph of human ingenuity, a reminder that our tools can now capture the universe's fleeting dramas. So, what does this mean for Neptune, for our solar system, and for the countless worlds beyond? Let's dive deeper. To grasp the scale of this event, we need to know Neptune. The 8th planet from the Sun, Neptune is a behemoth with a diameter nearly 4 times Earth's and a mass 17 times greater. Its gravitational pull dominates the outer solar system, sculpting the orbits of icy bodies in the Kuiper Belt and beyond. Yet, its distance, 30 times farther from the Sun than Earth, has kept it shrouded in mystery. Voyager 2's fleeting 1989 flyby gave us our first close-up, revealing a deep blue world of methane-tinted clouds, ferocious winds exceeding 1,500 miles per hour, and faint, dusty rings that pale beside Saturn's brilliance. Since then, astronomers have relied on telescopes like Hubble and now Webb to peel back Neptune's layers, tracking its storms and studying its 14 known moons, led by the enigmatic Triton. Neptune's atmosphere is a dynamic beast, a swirling mix of gases and ices where storms the size of Earth churn for years. Its deep blue hue, born from methane absorbing red light, gives it an otherworldly glow. But beneath this serene facade lies a turbulent world, one where winds whip faster than anywhere else in the solar system, and where the faint light of the distant sun barely warms its icy depths. This collision, however, revealed Neptune as anything but tranquil. The impactor's energy stirred its atmosphere, creating bright spots and disturbances in its cloud bands, temporary scars that may linger for decades. These changes, visible in Webb's follow-up images, images hint at the chaos unleashed when a massive object meets an ice giant's embrace. Why does this matter? Because Neptune isn't just a distant dot in the sky. It's a key to understanding our solar system's past and present. Its gravitational influence shapes the Kuiper Belt, a vast ring of icy debris left over from planetary formation. The collision suggests that this region is still active, with objects occasionally nudged into paths that lead to catastrophic encounters. This event wasn't a relic of the solar system's violent youth. It was a reminder that the cosmos is still alive, still evolving, still capable of surprises. What was this object that dared to challenge Neptune? Webb's data offers clues. The chemical signatures, carbon-based molecules, exotic ices like ammonia or carbon dioxide point to a body born in the solar system's outer reaches. It could have been a comet dislodged from the Oort cloud, a distant shell of icy bodies enveloping our system. Or perhaps it was a Kuiper Belt object, a chunk of primordial ice and rock flung inward by Neptune's own gravitational tugs. Either way, this wasn't a small asteroid. To leave a mark on a planet as massive as Neptune, it had to be substantial, possibly tens or even hundreds of kilometers across. Imagine this intruder's final journey. For billions of years, it drifted in the solar system's frozen outskirts, a silent wanderer in the dark. Then a subtle gravitational nudge, perhaps from Neptune itself or a passing star, sent it hurtling inward. As it approached the ice giant, Neptune's gravity seized it, accelerating it to tens of thousands of miles per hour. When it hit, it plunged into the atmosphere, compressing gases into shockwaves that lit up Webb's sensors. The energy released was unimaginable, rivaling the most violent events humanity has ever contemplated. Yet, in Neptune's gaseous depths, it left no crater, only a chemical echo, a scattering of debris, and a ripple of heat that may alter the planet's weather for years to come. This collision wasn't just a spectacle, it was a gift. The intruder's remains, now dispersed in Neptune's atmosphere, offer a rare chance to study material from the solar system's edge. The Kuiper Belt and Oort cloud are time capsules, preserving the raw ingredients of planet formation. By crashing into Neptune, this object made itself accessible, its chemistry glowing in infrared for Webb to analyze. Scientists are now racing to decode these signals, hoping to uncover clues about the solar system's infancy and the processes that built worlds like ours. For decades, Neptune has seemed a serene sentinel, orbiting quietly at the solar system's edge. But this collision shatters that illusion. The outer solar system is a restless place, where icy bodies dance in unstable orbits, nudged by the gravitational whims of giant planets. Neptune, sitting just inside the Kuiper Belt, acts as both shepherd and predator, stabilizing some orbits while flinging others into chaos. This impactor was likely a victim of that chaos, its path altered by Neptune's pull until it met its fiery end. This event underscores a profound truth. Our solar system is not a static museum, but a living, evolving system. Collisions, once thought confined to the solar system's violent youth, are ongoing. They shape planets, moons, and rings, delivering materials and stirring atmospheres. On Earth, impacts brought water and organic molecules, possibly seeding life. On Neptune, this collision may have enriched its chemistry, injecting compounds that could alter its clouds or storms. It's a reminder that the forces that built our world are still at work, playing out in real time on distant stages. The implications ripple beyond Neptune. Impacts are a universal process, shaping planets across the galaxy. Exoplanets, gas and ice giants orbiting distant stars likely face similar collisions. Webb's data from Neptune offers a blueprint for interpreting their atmospheres, where unusual chemical signatures or heat spikes might betray recent impacts. By studying Neptune, we learn to read the stories of worlds light years away, connecting our cosmic backyard to the broader universe. Neptune's collision didn't just affect the planet, it sent ripples through its delicate system of moons and rings. Neptune boasts 14 known moons, from the massive Triton, a captured Kuiper Belt object larger than Pluto, to tiny, irregular satellites barely resolved by telescopes. The impact's energy, while absorbed by Neptune's atmosphere, could have subtly altered the planet's gravitational field, nudging these moons' orbits over time. Triton, with its retrograde orbit and active geysers, is a prime candidate for study. activity? Could the collision have triggered new activity on its icy surface, or scattered debris that left faint marks? Neptune's rings, faint and dusty compared to Saturn's, are another potential casualty. The impact may have ejected material into orbit, feeding these tenuous arcs or creating new ones. Webb's infrared eye is now trained on these rings, searching for brightening or fresh dust populations, silent echoes of the collision. This raises a broader question. Are planetary rings often born or replenished by such events? Saturn's rings, thought to be relatively young, may owe their existence to similar cosmic catastrophes. Neptune's collision offers a live case study, a chance to watch a ring system evolve in real time. These changes, though subtle, could have long-term effects. Over centuries, the redistribution of mass and heat within Neptune might reshape its gravitational influence, altering the delicate dance of its moons and rings. Scientists are now monitoring these objects with renewed intensity, hoping to catch signs of orbital wobbles or new debris clouds. Each observation adds to a growing picture of a planetary system in flux, shaped by the violent whims of the cosmos. This collision is more than a singular event. It's a lens into planetary evolution. Impacts are a fundamental force, delivering materials, stirring atmospheres, and reshaping worlds. On Earth, they've reset life's course, from the asteroid that doomed the dinosaurs to earlier collisions that brought water to a barren planet. On gas giants like Neptune, their role is less clear, as the lack of a solid surface obscures direct evidence. But Webb's data changes that, offering a rare glimpse into what happens when a massive object plunges into a gaseous world. The energy from the impact penetrated deep into Neptune's atmosphere, potentially disrupting its ferocious winds or spawning new storms. Webb's images show unusual bright spots and elongated cloud bands, signs of turbulence unleashed by the collision. These disturbances could persist for years, offering a natural experiment in atmospheric dynamics. Scientists are also studying the chemical aftermath as the impactor's exotic ices mixed with Neptune's methane and hydrogen. These compounds, now glowing in infrared, turn Neptune into a laboratory for sampling the Kuiper Belt's chemistry, revealing secrets about the solar system's origins. Beyond Neptune, this event informs our understanding of exoplanets. Many distant worlds resemble Neptune in size and composition, orbiting far from their stars. Impacts on these planets could trigger storms, alter atmospheres, or even influence Moon's habitability. By decoding Neptune's collision, astronomers build a library of signatures, chemical spikes, heat bursts, cloud patterns that can be applied to exoplanet data. This bridges the gap between our solar system and the galaxy, turning a local event into a universal lesson. This collision also carries a sobering message for Earth. While Neptune's massive gravity makes it a cosmic vacuum, sweeping up debris, Earth relies on Jupiter and Saturn to deflect many potential threats. Yet impacts remain a reality, as evidenced by the dinosaur-killing asteroid 66 million years ago. Neptune's collision reminds us that the solar system is a hazardous place, with wandering bodies crossing planetary paths. By studying this event, scientists refine models of how objects travel inward from the Kuiper Belt or Oort cloud, improving our ability to predict and prevent impacts closer to home. Planetary defense is no longer science fiction. NASA's DART mission, which successfully redirected an asteroid in 2022, proved we can alter cosmic trajectories. Neptune's collision provides vital data for these efforts, showing how gravitational interactions guide objects into planetary collisions. It's a reminder that Earth's safety owes much to the outer giants, whose gravity absorbs threats that might otherwise reach us. But it's also a call to action, urging us to invest in monitoring and deflection technologies to protect our fragile world. Beyond science, this event carries profound philosophical weight. Neptune's collision reminds us that the universe is indifferent to permanence. Planets, serene for eons, can be reshaped in an instant. For humanity, tucked safely on Earth, this distant spectacle offers perspective. The forces that battered our planet billions of years ago still operate, ceaseless and impartial. Neptune, named for the Roman god of the sea, embodies this cosmic drama, a world of turbulent beauty struck by a fiery intruder. Its story rewritten in a moment. This discovery also stirs the imagination. For centuries, humanity has woven myths around the heavens, from comets as omens to gods hurling thunderbolts. Webb's capture of this collision feels like a modern myth, a tale of science and wonder converging. It inspires not just astronomers, but artists, writers, and dreamers who will weave this event into our collective narrative. It's a reminder that exploration is about more than data. It's about awe, about connecting with a universe that is vast, dynamic, and alive. Delving deeper into the collision's aftermath, we confront the tantalizing mystery of Neptune's interior, a realm as alien as the farthest reaches of the galaxy. Beneath its turbulent atmosphere lies a mantle of water, ammonia, and methane in exotic states. Supersonic water that flows like a liquid, yet holds a crystalline structure, and ices that conduct electricity under crushing pressures. The impact's energy, penetrating deep into Neptune's layers, may have disturbed these enigmatic regions, triggering subtle shifts in convection currents or heat flows. Webb's detection of persistent thermal glows suggests the collision's effects reached farther than expected, possibly stirring the planet's bizarre tilted magnetic field. This field, offset from Neptune's core, is already an oddity, and the impact may have sparked temporary changes in auroral activity or magnetic alignment, offering a rare chance to study the ice giant's hidden machinery. Scientists are now analyzing these signals, hoping to unlock clues about what lies beneath Neptune's clouds. A world of supersonic oceans and exotic chemistry that defies our earthbound intuition. This collision, in essence, has turned Neptune into a natural laboratory, where the interplay of impact energy and planetary physics reveals secrets that could redefine our understanding of ice giants across the cosmos. The collision also casts a spotlight on Neptune's role as a gravitational architect, orchestrating the delicate dance of the Kuiper Belt. This vast reservoir of icy bodies stretching beyond Neptune's orbit is a relic of the solar system's formation, a frozen archive of primordial material. Neptune's gravity shapes this region, locking some objects in stable resonances while nudging others into chaotic paths. The impactor, likely a Kuiper Belt wanderer, was a product of this cosmic choreography. Its orbit destabilized until it plummeted into Neptune's embrace. This event raises profound questions about the Kuiper Belt's long-term evolution. Are such collisions part of a gradual pruning process, where Neptune slowly clears its neighborhood of debris? Or do they hint at ongoing disruptions, perhaps triggered by distant gravitational influences like passing stars or unseen planets? By modeling the impactor's journey, scientists can trace its origins, piecing together the subtle forces that keep the outer solar system in motion. This collision, then, is not just a singular drama, but a chapter in a billion-year saga of gravitational tugs and cosmic collisions, with Neptune as both conductor and stage. Zooming out, Neptune's collision echoes the violent processes that birthed our solar system. Billions of years ago, planets formed through relentless impacts, as dust and gas coalesced into worlds like Earth, Jupiter, and Neptune itself. The moon was born from a Mars-sized impactor striking Earth, while Uranus's tilted axis bears the scars of a similar catastrophe. This recent collision, though smaller, mirrors those ancient events, offering a modern glimpse into the chaos of planetary formation. The impactor's disintegration into Neptune's atmosphere may have delivered complex molecules, hydrocarbons, nitrogen compounds, or frozen volatiles, mimicking the processes that seeded Earth with the building blocks of life. By studying the chemical fallout, scientists can test theories about how impacts shaped early planets, delivering water and organics to nascent worlds. This event transforms Neptune into a time machine, connecting the solar system's turbulent youth to its present-day dynamics. It's a reminder that the forces of creation and destruction are timeless, playing out across the cosmos in an endless cycle of collision and renewal. The collision's impact on Neptune's atmosphere extends beyond immediate chemical and thermal scars, potentially unleashing phenomena akin to atmospheric tsunamis, massive waves of pressure and gas that ripple across the planet's turbulent skies. Neptune's winds, already the fastest in the solar system at over 1,500 miles per hour, are driven by complex internal dynamics that remain poorly understood. The sudden injection of energy from the impactor could have amplified these winds, creating instabilities that cascade into giant rolling disturbances. Webb's images have revealed intriguing patterns, shifting cloud bands, elongated vortices, and bright spots that pulse with unusual intensity. These may be the signatures of atmospheric waves, triggered by the collision's shockwaves, that propagate across latitudes, reshaping Neptune's weather in ways that could persist for decades. For scientists, this is a golden opportunity to study how gaseous planets respond to sudden disruptions, offering insights into atmospheric physics that apply not only to Neptune, but to exoplanets with similar compositions. By modeling these disturbances, researchers can refine climate models, shedding light on how energy injections, whether from impacts or stellar flares, shape the long-term evolution of planetary atmospheres across the galaxy. Neptune's largest moon, Triton, adds another layer of intrigue to this cosmic saga. Larger than Pluto and likely a captured Kuiper Belt object, Triton is a world of icy geysers and a retrograde orbit that hints at a violent past. The collision with Neptune could have sent subtle shockwaves through its gravitational system, potentially affecting Triton's delicate balance. Debris from the impact ejected into orbit might have peppered Triton's surface, leaving fresh craters or depositing exotic compounds that alter its icy chemistry. Webb's infrared gaze is now trained on Triton, searching for signs of new geological activity, perhaps intensified geyser eruptions or faint dust clouds stirred by secondary impacts. These changes could reveal how moons respond to their parent planet's traumas, offering a glimpse into the long-term interplay between Neptune and its satellites. Triton, already a geological oddity with its nitrogen-driven plumes, may hold chemical or orbital traces of this event, turning it into a natural archive of the collision. This connection underscores the idea that planetary systems are interconnected, with impacts rippling through moons, rings, and atmospheres in a delicate cosmic dance. The collision on Neptune serves as a universal blueprint, illuminating processes that likely shape planets far beyond our solar system. Thousands of exoplanets, many resembling Neptune in size and distance from their stars, have been cataloged, but their atmospheres and histories remain enigmatic. Some show puzzling features, unexpected heavy metals, anomalous methane levels, or transient heat spikes. Neptune's collision suggests that such signatures could stem from impacts, where infalling bodies pollute atmospheres with new chemistry or trigger temporary storms. Webb's detailed data from Neptune, chemical enrichments, thermal glows, and cloud disruptions provides a reference for interpreting these distant signals. By comparing Neptune's post-impact signatures to exoplanet spectra, astronomers can distinguish between stable planetary processes and the fleeting scars of collisions. This event thus transforms Neptune into a Rosetta Stone for exoplanet science, bridging our solar system to worlds light years away. It's a reminder that the universe is a tapestry of violent encounters, where impacts sculpt atmospheres, alter climates, and perhaps even set the stage for habitability on distant moons, connecting our cosmic neighborhood to the broader galactic story. As Neptune recovers, scientists are watching for long-term effects. The injected heat and chemicals could spawn new storms, alter cloud structures, or intensify auroras. The rings may brighten, and moons like Triton may show subtle changes in their orbits or surfaces. Webb's ongoing observations will track these shifts, turning Neptune into a decades-long experiment in planetary change. Each data point adds to a story that began with a collision, but will unfold across generations. This event also argues for renewed exploration. Voyager 2's 1989 flyby left us hungry for more, and Webb's discovery proves Neptune is worth revisiting. A dedicated orbiter, equipped to study its atmosphere, moons, and rings up close, could reveal the collision's lasting impacts. Such a mission, inspired by Webb's data, could answer lingering questions about Neptune's interior, its magnetic field, and its role as a gravitational architect. It's a call to push further, to explore the outer solar system with the same boldness that sent Voyager to the stars. Neptune's collision is more than a scientific milestone. It's an invitation to marvel at the universe's grandeur. What does this event mean to you? Is it a glimpse into the solar system's restless heart, or a warning of cosmic hazards? Maybe it's a spark of wonder, a reminder that even the farthest worlds hold stories waiting to be told. Drop a like if this tale of fire and ice captivated you, and share your thoughts in the comments. Do you think Neptune's collision hints at more surprises in our cosmic backyard? Subscribe for more journeys into the universe, where every discovery brings us closer to understanding our place in the cosmos. The stars are calling. Let's answer together.